we are going to start module 3 of chapter 6. In this module, we shall discuss the condition for canonicality. So far, we have discussed detail about the Hamiltonian mechanics and found that Hamilton's equations of motion cannot provide much more advantage if we consider it in normal form, but its utility can be increased if we can transform the normal Hamiltonian form into a form of our choice. With the help of canonical transformation, we can get this result. Canonical transformation needs a condition for canonicality. So, in this module, we shall discuss and derive this condition. In this module, we shall discuss the condition for canonicality and will derive this condition, and will use this condition to test for canonicality. First of all, let us now discuss about the configuration space and phase space. We shall recall it again. The instantaneous configuration of a dynamical system is described by the generalized coordinates. The n generalized coordinates small q1, small q2 up to small qn correspond to a particular point in the n-dimensional space. The n-dimensional space spanned by these n generalized coordinates of a dynamical system is called the configuration space of that system. The state of the system changes with time, and the system point traces out a curve in moving through the configuration space. The curve traces out by the system point is known as the trajectory. On the other hand, the phase space is spanned by the generalized coordinates as well as generalized momenta. So, its dimension is 2n dimension. At any instant of time, the system represented by a point in phase space is called the phase point. According to the physical laws of the system, phase point moves with the time. As the phase point travels through the phase space, a path is traced by it. This path is known as phase curve. The phase space transformations which preserve the Hamiltonian form of equations of motion are known as canonical transformation. Now, we shall search the condition for canonicality. The transformations from small q, small p and t to capital Q, capital P and T defined by capital Qi equal to capital Qi function of small q1, small q2 up to small qn, small p1, small p2 up to small pn and t, and capital Pi equal to capital Pi function of small q1, small q2 up to small qn, small p1, small p2 up to small pn and t for I equal to 1, 2 up to n may be canonical if Hamilton's principle can be written as delta integration T0 to T1 summation over I equal to 1 to n small pi into small qi dot minus capital H function of small q, small p, t into dt del equal to delta of integration T0 to T1 summation over I equal to 1 to small n capital Pi into capital Qi dot minus capital K function of capital Q, capital P, T dt. must be satisfied in both the new, that is capital Q and capital P, and the old phase space coordinates, that is small q and small p, in order to preserve the form of canonical equations of motion. But the two integrands in the following equation can differ at most by a total time derivative of a function which is coordinates and time, whose variations at times t0 and t1 vanish. That is, delta of capital F1 function of t0 equal to delta capital F1 at t1 equal to 0. Since we know that delta of integration t0 to t1 first order ordinary derivative of capital F1 with respect to time t into dt equal to delta of capital F1 at t1 minus capital F1 at t0 vanishes. Therefore, we can generalize the following requirement on the transformations 6.3 as delta integration t0 to t1 summation over I equal to 1 to n small pi into small qi dot minus capital H into small q small p t to dt equal to delta integration t0 to t1 summation over I equal to 1 to small n capital pi into capital qi dot minus capital K function of capital Q capital P t plus first order ordinary derivative of capital F1 with respect to time t equal to 0. Here capital F1 is a function of small q, capital Q and t. The two integrands in 6.5 are related by the relation which is given by 6.6 we have already obtained in previous module. Here lambda is a scalar factor known as valence of canonical transformation. When lambda not equal to 1, the transformations are called extended canonical transformation. Now, we shall use this relation in searching the condition of canonicality. Let us consider the condition of canonicality given in terms of generating function already obtained, which is summation over I equal to 1 to n small pi into d of small qi minus capital H function of small q small p t dt equal to summation over I equal to 1 to n capital pi into d of capital qi minus capital K function of capital Q capital P t into dt plus d of capital F1 function of small q capital Q t. Here we have used the result qi dot equal to ddt of small qi, whereas capital Qi dot equal to ddt of capital Qi, and using this result we have obtained this equation. Here d of small qi and d of capital Qi are the perfect differential in coordinates which occur in real time dt. Since the transformation in the phase space are essentially geometrical, which means without any change of the time parameter t, we can set dt equal to 0 in the above equation. Setting dt equal to 0 in the above equation, we get summation over I equal to 1 to n small pi into delta qi minus capital Pi into delta capital Qi equal to delta capital F1 equal to an exact differential. Please note that in our previous expression we have used the notation dqi for variation. As we have used dt equal to 0, so in this equation we have used Kronecker delta sign. Here the parameter t is held constant in capital Qi function of small q small p t, capital Pi function of small q small p t, and capital F1 which is a function of small q capital Q t, while finding the differential delta small qi delta capital Qi delta capital F1. The above equation gives a necessary as well as sufficient condition for a transformation given by capital Qi equal to capital Qi function of small q small p t, capital Pi equal to capital Pi function of small q small p t for I equal to 1, 2 up to n to be canonical transformation for fixed value of time t. Now, the condition for canonicality can be derived in other forms involving the other principal forms of the generating functions capital F2 which is a function of small q capital P and t, capital F3 which is a function of capital Q small p and t, and capital F4 which is a function of small p capital P and t. In a similar fashion we can get the following conditions: summation over I equal to 1 to small n small pi into delta small qi plus capital Qi into delta capital Pi equal to delta capital F2 equal to an exact differential. Next we get summation over I equal to 1 to n small qi into delta small pi plus capital Pi into delta capital Qi equal to delta capital F3 equal to an exact differential. We have obtained the result using the relation between the generating functions capital F1 and capital F3 which have already been discussed in previous module, that is module 2 of chapter 6. If we use the relation between the generating functions capital F1 and capital F4, we shall get the condition for canonicality as summation over I equal to 1 to small n small qi into delta pi minus capital Qi into delta capital Pi equal to delta capital F4 equal to an exact differential. We have obtained the condition for canonicality which is very much essential in classical mechanics, particularly in Hamiltonian mechanics. To get advantage from Hamiltonian mechanics, we need it. So, using the different types of generating functions, we have obtained the necessary and sufficient conditions for canonicality. Now, we shall use this condition to solve some problems. Let us consider first problem. Prove that the transformation given by capital Q equal to log sin p divided by q, capital P is given by small q into cot p is canonical. To prove the canonicality, we have to prove small p into d of small q minus capital P into d of capital Q is an exact differential. Let us check it. Now, small p into d of small q minus capital P into d of capital Q gives small p into d of small q, and in the second term we are replacing capital P from the given expression and we are calculating the differential from the expression of capital Q. This has been written in the second term of the right hand side. Now, calculating the differential, we get 1 divided by sin p divided by small q into d of sin p divided by small q. The first term has been written as it is and the coefficients of the differential part has been written as it is. After taking the derivative, we get q cos p into dp minus sin p into dq divided by q square, which have been written in the right hand side of the second term, and we finally get small p into d of small q minus capital P into d of capital Q is equal to small p into d small q minus small q square cos p divided by sin square p into q cos p into dp minus sin p into dq divided by q square. On simplification, the right hand side portion can be written as small p into dq minus q into cot square p dp minus cot p into dq, which can be written in explicit manner. In the second line, it has been written combining the terms of like terms, we get the third line. Now, p into dq plus q into dp is written here and cot p into dq is written as the third term. 1 minus cosec square p gives q minus q cosec square p, q has been written here. So, we have only minus q cosec square p into dp. First two terms of the above line can be written as d of pq and the next two terms can be combined as d of q cot p. So, finally, we have small p into dq minus capital P into d of capital Q is equal to d of q into p plus cot p, which is an exact differential. So, the transformation is canonical. Consider next problem. Show that the following transformation is canonical, where capital P and capital Q have been given. To prove the transformation is canonical, we have to prove that small p into d of small q minus capital P into d of capital Q is an exact differential. Let us test it. If we replace capital P from the given expression and taking the differential of capital Q, we get the second term in the right hand side of the equation. Taking the differential, we get the next line. After simplification, we can get the third line. These three terms in the third line on the right hand side can be combined as d of p q divided by 2. So, the left hand side p into d of small q minus capital P into d of capital Q is an exact differential. So, the given transformation is canonical. Consider the third problem. If the equations for the transformation between the two set of coordinates are given by capital P equal to 2 into 1 plus root q cos p into root q sin p, capital Q equal to log of 1 plus root q cos p, show that the transformation is canonical. We have to show that small p into dq minus capital P into d of capital Q is an exact differential. Substituting capital P and capital Q from the given expression, we get the right hand side portion. After calculating the differential, we can get the next line. On simplification, we get the third line. After substituting the differential of root over q into cos p, we get the third line, which can be simplified and written in the fourth line of the right hand side. Now, we have small p into d of small q minus capital P into d of capital Q equal to small p minus half sin 2p into dq plus capital Q into 1 minus cos 2p into dp, which can be written as given in the right hand side portion in the differential form d of q into small p minus half sin 2p. So, the given transformation is canonical. Now, we shall define contact transformation. If the transformation which connects the set of variables small q1, small q2 up to small qn, small p1, small p2 up to small pn and capital Q1, capital Q2 up to capital Qn, capital P1, capital P2 up to capital Pn, such that capital P1 into d of capital Q1 plus capital P2 into d of capital Q2 plus up to capital Pn into d of capital Qn minus small p1 into d of small q1 plus small p2 into d of small q2 plus up to small pn into d of small qn is a perfect differential of a function which is small q1 q2 up to qn and small p1 small p2 up to small pn, then the transformation is called contact transformation. Here the variables small q1, small q2 up to small qn are the generalized coordinates, whereas small p1, small p2 up to small pn are the generalized momenta. The geometrical property which is essential for contact transformation is if one draws two curves meeting tangentially at a point, then in the transformed phase space the corresponding curves are also bound to meet tangentially at the corresponding point on the phase space. This signifies the meaning of the term contact. If the time parameter is not transformed, all the canonical transformations are contact transformations. If we consider the Hamiltonian in a normal form, then it cannot reduce the difficulties in problem solving, but using a transformation If we can transform the Hamiltonian in our desired form, then we can get advantage from this. For this reason, we need a transformation which can preserve the form of Hamiltonian. In this module, we have already obtained such type of condition, and in terms of different generating functions, we obtained the conditions.